Hi, good evening everybody. So I wanted to make a video tonight to show you how to balance reactions in acidic solution, balance a redox reaction in acidic solution. And so I've got two examples I'm going to go through, and I'm going to follow the same steps that we talked about in class, and hopefully this will become a system for you that's pretty logical. I've picked a couple of reactions that involve high numbers of electrons because everything we've done so far has been a low number of electrons, but I still want to show you that it's still possible either way. So the first thing we need to do when we work our way through this is we need to assign oxidation numbers to everything. So when we assign the oxidation numbers, sorry to move some things out of the way here, we're going to start with each of these elements here, knowing the rules that we have. So hydrogen we know is almost always going to be +1 unless it's attached to a metal, in which case it's -1. So there are two positive ones there, which makes the sulfur a -2. Going on to the nitrate, we've used nitrate a lot, but we can see that the oxygen is going to be -2 because it always is. There are three of them for a total of -6, which means the nitrogen becomes a +5. Moving over here, sulfur, we can see it's a standalone element, so itself is going to be 0. Our oxygen here in the nitrogen monoxide is going to be -2, and therefore the nitrogen is going to be +2. So now what we can do is we can see where these substances are going to connect with each other. And we can see that the sulfur in the hydrogen sulfide goes from -2 to 0. So that's going to be one of the processes we're going to talk about. To go from -2 to 0, there has to be a loss of electrons. It's getting more positive, so therefore that's your oxidation. And then for the other substances, we can see that the nitrogen went from +5 to +2. And to do that, it had to gain 3 electrons, so that is your reduction. Okay, and so now what we can do is we can balance each of our oxidation and reduction half reactions. We'll start with the reduction half reaction, and we can say that NO3 minus becomes NO. And so when we are taking a look at the half reactions, remember the first thing we want to do is we want to try to balance the mass. And so we can write down our oxidation half reaction here as well. We've got H2S, which becomes S8. So we'll start with our NO3 reaction. I'll change colors to purple here. We can see NO3 becomes NO. So first thing we're going to do is balance our mass with everything except for our oxygen and hydrogen. So the nitrogen, we have 1 and 1, so that's all good. Now we want to balance our oxygen. So the way that you can add oxygen is you can remember this happens in aqueous solution, and because it's an aqueous solution, we know that there's going to be water present. So for every oxygen we need, we're going to add 1 water. We've got 3 oxygens on this side, 1 oxygen on this side, so therefore we're going to add 2 H2O. Now we can see to balance that out, we have to remember this is happening in acidic solution. We can see that there are 2 H2Os, which means there are 4 hydrogens involved. We go to the opposite side and we balance with 4 H pluses. So that's all set there. We take a look at our second half reaction. We can see the oxidation side. H2S becomes S8. We can see that there are 8 sulfurs here and 1 here, so we need a coefficient of 8 in front of this, which now gives us the 8 sulfurs. But the problem is now we've got the hydrogens here that we've unbalanced, and we didn't have any at all. So what we can see is that there are going to be 16 hydrogens. So on this side we're going to therefore make it 16 H pluses. All right, so now the next step we want to do is we want to go through and we want to balance our charge. So to balance the charge, we want to look at the total charge on each side of the reaction. For the reduction half reaction, we can see 4 pluses and 1 minus gives you a total of 3 plus. On the product side of the reduction half reaction, we have 0 charge here and 0 charge here for a total of 0. And so therefore, to balance the 3 plus with a 0, we're going to add 3 electrons on this side of the half reaction. Okay? Let's take a look at the second half reaction. We've got 0 on the reactant side. We've got 16 plus on the product side. So we've got 16 plus here, and we've got 0 here. We want those to equal out, and so therefore we're going to add 16 electrons on this side of the half reaction right here, which will balance that out. And so now what we can do is we can see that, erase these here, we can see that the two sides of each of the half reactions are balanced by mass and charge. The last step is to make sure that the two half reactions are balanced with each other. And to do that, you want to make sure the electrons are the same. So we need to think about what is the multiple that 16 and 3 have in common, and unfortunately, it's 48. So what that means is we're going to have to take and multiply the first reaction by 16, and we're going to have to take and multiply the second reaction by 3. And so when we do that, what we get is 48 electrons plus 4 times 16, which is 64 H pluses, plus 16 NO3 minus yields 16 NO plus 16 times 2, which is 32 H2O. Okay, I told you that this one was going to be pretty large with respect to the coefficients. For the oxidation half reaction, we can see 3 times 8, which is 24 H2S yields 3 times 1, 3 S8 plus 3 times 16, which is 48 H pluses, plus 3 times 16, which is 48 electrons. And now the last step is we want to put our half reactions back together again, and we're going to recognize that the number of electrons here and the number of electrons here are going to balance out with each other, so we're not going to even include them. So what we're left with are 64 H plus 16 NO3 minus plus 2 H2S yields, we're going to go to our product side, 16 NO plus 32 H2O plus 3 S8 plus 48 H plus. Okay? Now the last step in this process is we need to recognize that we need to combine any terms that are alike on both sides of this equation. In math, we'd call that combining like terms. You can see 48 H pluses here, and we can see 64 here. So what we'll do is we'll subtract 48 H pluses from both sides of that reaction. So 64 minus 48 H plus. It'll cancel it out on this side. And what are we going to be left with? Well, it works out to be 16. 16? Yeah, 16. So what we're left with for our final answer is 16 H plus 16 NO3 minus plus 2 H2S yields 16 NO plus 32 H2O plus 3 S8. And that right there is the balanced redox reaction for this process. Okay. Again, the coefficients were large as we worked our way through, and the number of electrons were large. Let's take a look at a second example right here. And don't forget, you can pause this video if you have to. So we've got MnO4 minus plus CH3OH, methanol, yields HCOOH, which is formic acid, plus Mn2 plus. So the first thing we want to do is assign oxidation numbers. -2 times 4 is -8, which means the manganese plus 7. In CH3OH, we got a little bit of a mess here. We know that the oxygen is going to be -2 and each hydrogen is going to be +1. Okay, so we end up with +1 here and +3 here for a total of +4. So you get a +4 for all of your hydrogens, -2 for your oxygen, so therefore it's got to be -2 on your carbon. With our formic acid, same process, +1 for your hydrogens on each side, -2 for each of your oxygens. So you've got -4 here, -2 is -4, plus +2, which makes it -2, which makes this carbon have to be +2, okay? And the manganese becomes +2, all right? Rewind and stop and look at these again if you need to for some reason. Now what we can see is we've got some oxidations and some reductions happening here. You've got your manganese go from +7 to +2, and that's a reduction. To go from +7 to +2, you have to lose electrons. And then you've got your carbon, which is going from -2 to +2. In order to do that, you have to lose electrons, so that's your oxidation. So now we'll set up our two half reactions. First, the oxidation half reaction, which is going to be your CH3OH yields HCOOH. And then we've got our reduction half reaction, which is going to be your MnO4 minus becomes Mn2 plus. So now we can take each of these and independently balance what's going on with them. So we're going to take a look at the methanol to formic acid first. We're going to first balance the carbons. We can see that there's one carbon here and one carbon here, so that's all set. Now we're going to balance our oxygens. You've got 2 oxygen here and 1 oxygen here, so we need another one, so we're going to add an H2O on this side. So now we're going to balance our hydrogens. We look at this side, you've got 2, plus 3 is 5, plus 1 more is 6, so there's 6 hydrogens on this side, and only 2 on this side, so therefore we need to add 4 H pluses onto this side to balance that out. With a permanganate, you can see the permanganate to manganese 2+. The manganese you can see balances with no problem. You have your 4 oxygens here, so therefore you're going to add 4 H2O on this side. And now you've got the 8 hydrogens here that are unaccounted for, so we're going to go ahead and put 8 H pluses on this side. So now we'll go through and we will balance our charge. You can see the charge on this side is 0 here and 0 here for a total of 0. You can see 0 here and 4 plus here for a total of 4 plus. So to get 4 plus and 0 the same, we're going to add 4 electrons to this side. For your reduction half reaction, you have 8 plus and 1 minus, which is a total of 7 plus. You've got 2 plus on this side for a total of 2 plus, and therefore how are you going to balance 7 plus with 2 plus? You're going to add 5 electrons on this side. So now we can go through and we can get rid of these here because that was just our work to show what was going on. And now we need to balance the half reactions with each other. So you have 4 electrons here, 5 electrons here. The only common multiple that 4 and 5 have in common is 20. So we're going to take and we are going to multiply the top reaction by 5, and the bottom reaction will multiply by 4, so that we have 20 electrons on both sides. And so if you bear with me this time, I'm just going to write it down as we combine the 2 reactions together. So what we're left with here, and I'll try to get a color here that we can differentiate. I guess we'll go with blue. We end up with 5H2O plus 5 methanol, CH3OH. That's your 2 reactants here, plus, remember, we're going to leave the 20 electrons alone because we know that they're going to cancel. The 5 times 4 is 20 and the 4 times 5 is 20, but 4 times 8, which is 32H plus 4 permanganates, MnO4 minus, yields. Now we're going to go to our product side. 5 times 1, it's going to be 5 formic acids, HCOOH, plus 5 times 4, which is 20 H pluses, and there's your 20 electrons. We're going to leave those alone, plus 4 times 1, 4, Mn2 plus 4 times 4, which is 16 H2O. And now we want to combine our like terms here. And we want to be careful here. This is 20 H pluses, not 2 OH pluses. That would be weird. That doesn't even exist. But to combine these like terms, we can see we have 32 H pluses here and 20 here. So these all go away. And this 32 is going to be 32 minus 20, or 12 H pluses. I don't know if that yellow is a little bit hard to see. And that's pretty much all it can combine. So what we are left with here is our final reaction. We'll put the final reaction in red. What we're left with is 5H2O plus 5 CH3OH plus 12 H plus. Oh, I already found a mistake. Let's back up here for a second. You got a little bit too hasty here. I knew something wasn't looking right. Let's go back to yellow. We can see the 5 H2Os here and 16 here. These 5 are going to go away. Oops, let's not do it that way. These 5 are going to go away. We're going to subtract 5 here, which is going to leave us with 11 H2O. Now we can recombine those 2 reactions. I'm doing it in red here. 5 methanol CH3OH plus 12 H plus 4 MnO4 minus yields 5 HCOOH, which is formic acid, plus 4 permanganate ion. 4 manganese 2 ions plus 11 H2O. And that right there, friends, is your final balanced redox reaction. Okay, hopefully this was helpful for you, and hope you are able to get something out of this. Have a good night.